Welcome to Crop TV, Iowa State University, on a topic heavy equipment soil compaction measurement, modeling, effect on crop yield responses. I'll go through this presentation doing a brief introduction and then uh, doing the soil compaction from a vehicle loading using a modeling approach, and then describe about crop yield effect. This work is from a group Soil Machine Dynamics Laboratory at Dr. Takashi's lab at Ag and Biosystems Engineering at Iowa State, Ames, Iowa. In the laboratory, we try to integrate modeling approach, laboratory indoor control testing, and field validation of machine systems for soil management, tillage, and its relationship to crop yield. At the Soil Machine Dynamics Laboratory, located at Iowa State in Boone, Iowa, there are 3 state-of-the-art equipments that would do studies on wear research, soil compaction, tillage tools design. They're automated. Tests could be controlled manually or automated. The whole idea is to do a controlled laboratory 27/4 study on soil to machine interaction for performance, design, and wear. Back in 2013, there was a farmer's perspective on soil compaction research question, which was also done in 1993. And if you look at this survey data, if we pay attention to what is related to soil compaction, we could look at top 3. They involve either working on wet soil that could impact compacting the soil, or concerned with heavy machinery on soil health and wheel traffic pattern control, can be used as a method to reduce soil compaction. So on average, we're looking at close to 59% of the responding feedback ranked those on top. There was also another one which was ranked a little bit close on the bottom, 42%. It says, I consider the weight of agricultural machinery as I make decisions on new equipment purchases. So it's kind of interesting because if we look at heavy machinery affecting compaction, working on wet condition with poorly wheel traffic management, the weight would have been on the top as well. But weight of agricultural machinery is related to either wider machines, bigger machines, which helps productivity, completing the work in the field in a relatively shorter period of time. But the negative impact of going bigger and heavier machines could be significant on soil compaction. A similar question that was done in 1993, 59% say that soil compaction is important when you judge soil health. And with this new survey, there was about 74%. What this shows is that the relationship between soil compaction and causing a soil health had increased, and partly due to the climatic variability where growers would go into unfavorable soil conditions, mainly wet soils, with the heavier machines. So as we try to look at, managing soil with modern equipment machinery, what we are trying to do is to develop a standard way of measuring footprint from attractive devices. There is no standard footprint measurement, partly because the foot measurement that manufacturers would do on a hard surface is not standard, and it's not comparable when you try to compare track versus pneumatic tires, because tracks have a rigid or stiff drive system, the lugs are stiff, where pneumatic tires, they have a tire and there's a volume of air inside it, where reducing the tire inflation could benefit increasing the contact area or reducing soil compaction. Because of this lack of a standard measurement of footprint, which really is where the start of soil compaction starts at the ground. The wider the footprint, there's a reduction in soil compaction. For that, we are also, trying to develop a standard way of measuring footprint with artificial soil at the Soil Machine Dynamics Laboratory. I would go through research that we have been doing on how soil compaction relates to crop yield, both modeling approach and also a field measurement. The key highlights out of a 3-year study on corn that we did at Iowa State, there is a benefit about 4.4% yield increase when you choose a newer tire technology, IF and VF. They're new standard tires that have a higher deflection. IF supports 20% vertical load at the same tire inflation pressure to a standard radial tire. VF supports 40% vertical load as compared to the standard radial tire. But their effect on soil compaction and crop yield has not been done. And that's what this study is trying to highlight, that mainly on the crop yield effect. With the study, I'll go in detail, but the tires on that tractor, dual front and rear, had IF tires, and on that planter, 24-row, 30-inch row spacing, the tires are VF tires. We also had another treatment, a central tire inflation system. When someone has a tire inflation management built on a tractor, the tire inflation pressure can be precisely adjusted depending on transport load or field load and transport speed and field speed. For planting applications, the 24-row and folded in the field would run at a lower speed and a lower load on the transport tires compared to a tractor that has 24-row planter on the back folded on the road. You got a higher road speed and a higher load on the transport tires of that planter. So if we manage the tire inflation pressure depending on the precise load in the field and speed with a central tire inflation pressure, what would be the effect on yield? Another one that is ongoing research at Iowa State with the ag engineering farm is, how about those new tire technologies? What's their effect on compaction induced from pre-emergence or early emergence sprayer applications? With this one, it's with a large flotation tires, 720 nominal section width. What we found was that the trafficked row of that plant, which is the center of that tire, the crop starts to have stagnant growth at emergence. And also we look at the ear at harvest. There were some ears that did not have grain, and the variation among the ears in terms of their potential maximum yield and also ear characteristics had a higher variability on the trafficked rows compared to the untrafficked row, which is the center of that sprayer machine that did not see traffic during the sprayer application at the early stage of that plant. So if you have a tire inflation pressure management or a newer tire technologies that has a higher contact area, how much would be the benefit by using this new tire inflation pressure management or newer tires compared to the standard radial tire, which deflects less than the newer tire technologies? Now, when we look at compaction, either from its effect on soil or its effect on crop yield, it is a probability of events. The high likelihood of creating compaction would be when machine is trafficking on the field at a higher moisture content. Especially if we look at plastic soil consistency, where you would roll your soil and it would start to crack about 1/8 of an inch, that is a plastic soil condition. Anything around that moisture condition would create a high likelihood of soil compaction. Another one is a high tire soil pressure system. Higher tire inflation pressure tend to create a higher pressure at the ground, which would create a more higher tendency of soil compaction. So if you do the combination of wet soil, heavy load, and also a high tire inflation pressure, those are the two or three, if you add axial load, that would create a highly likelihood of soil compaction. Another one is the traffic management in the field. A high percent of field traffic would create soil compaction. Now, if we look at management, which is preventing soil compaction, there are two options trying to properly manage tire inflation pressure or field trafficking. When you think about you have an operation to do and you cannot control the soil condition, either due to timeliness of the operation for planting, for example, or crops need to be harvested because they are mature, trying to minimize operating in a field when it is closer to plastic limit. Finally, understanding how either the soil conditions or the machine systems would affect soil and crop yield has not been done as much in the 80s or 90s, even though the feedback from growers has shown about 79% of survey data shows that there's a concern from soil compaction on soil health, and our machine sizes in the field are getting heavier and bigger equipments are used. There's a very limited study on the current modern machine sizes, tire technologies on soil and crop. So our approach is to leverage or also use simulation and modeling to provide understanding of how load applied on soil and soil responses to the load could help either in the earlier design of soil compaction, managing tools, or reducing soil compaction at what condition. It will also help in somewhat a decision support for conditions where how much will be the impact on soil compaction if the working conditions change. So we try to integrate both modeling and simulation approach as a decision support and also field research to quantify the impact. So I'll go through the study that we have been doing, still going on how to leverage simulation and modeling, because simulation and modeling has a limitation in quantifying accurately the results, but it still within reasonably acceptable error, it could still provide the understanding and decision support. When you think about machine loading of soil compaction, in doing it, what we're looking at, vehicle load is transferred through the tractive devices to the soil at a given area where the pressure distribution could vary. If you have a high tire inflation pressure, most of the pressure will be distributed at the center of the tire. When you reduce the tire inflation pressure to some extent, underinflated, the pressure distribution from the tire on the soil will get higher on the legs compared to the center. So that is the modeling or creating the loading condition, the pressure transferred from the load on the ground, and the pressure distribution. When that load is applied, the soil responds. First, the stress of the soil propagates deep inside the soil profile, which is a function of the load or the wetness of the soil. So the wetter the soil, the deeper the compaction would go compared to a hard or drier soil. Then once the compaction is transferred from the load or the pressure at the ground to a soil stress, the soil stress is defined as the intensity of the force applied on a soil, and the soil responses, we call it in engineering a strain or compaction, which would require some kind of soil compaction model to find the relationship between the strain and the stress applied, which is a function of the material properties of the soil. So soil compaction for modeling purposes could be expressed as a strain, which is how much change it has in its volume before the load and after the load at a different soil depths, or if there are soil samples taken from the field and calculate the porosity, which is how much pores is in a bulk of a soil occupied by the air and the water, or a bulk density, which is the volume of soil holding the mass, and it's expressed as mass per unit volume of the soil. Another good way of measuring soil compaction in the field is a soil cone penetration resistance. It's an indirect way of measuring compaction. Probing a ASAB standard cone, which is 30-degree cone with a diameter, one of them is 0.5 inches. Probing that at a constant speed, a softer soil will resist less, creating lower penetration resistance. A harder soil or compacted soil would have a higher penetration resistance to the standard probe, and that would be used as a way to quantify soil compaction. So it's through this load applied, load distributed at the surface, load propagated as a soil stress converted to soil strain that will quantify the soil compaction. So for engineering, it's really what you're measuring is a strain, but strain can be converted to porosity or bulk density if you know the initial condition. So cone penetration resistance is an indirect way of measuring it. So leveraging the modeling and simulation approach, we compared a modern sizes of machines with a tire inflation pressure recommended by the tire manufacturer for the nominal loads and sizes. We look at tractor that has duals, both front and rear, and also singles. Compare it with harvesting platform with duals on the front and single on the back. And grain cart has tire and also track with a 1,000 bushel capacity. So I will show a result on two things. One is the effect of tire inflation pressure on a normalized soil vertical stress, which is an indicator of the degree of soil compaction for the 8 cases of machines, tractor, combine, single rear, dual on a combine, and then the grain cart. Now, if we look at the result of this simulation, what we found was that the normalized soil vertical stress at 6 inch and 12 inches, the highest came from the grain cart and the combine in a relative scale to the tractor, and the higher compaction occurred at the 12 inches compared to the 6 inches. And this is very important because the deeper the compaction, either a grower would spend more energy to break it, or sometimes it might be beyond what a typical tillage depth a grower can apply. This modeling approach helps what kind of tire inflation pressure management would create a compaction scenarios, top 6 inches, at the 6 inches and 8 inches stress measured. So the point is that a higher tire inflation pressure that would be applied to support a higher load would create more compaction, with a case where the grain cart that had a track created lower ground pressure and lower compaction than the wheel. So I look at, in the earlier slides, the effect of tire inflation pressure on normalized soil vertical stress as an indicator of soil compaction. Here, what we're showing is how about the mass in US ton per axle of this different fleet of machines and their tractive devices on soil compaction. There were a lot of studies in the 80s in the temperate climate, including Europe and Northern America. From those studies, a conclusion was made that limiting the axle load 10 ton per axle would be very beneficial for managing soil compaction. If axle load exceeds 10 metric ton per axle, it could create a deeper compaction below 20 inches compared to what you would do at the lower axle load. But that limit really, a lot of the modern machines, we passed it in the early 90s or mid 90s. In this study, if we look at it, tractors are still, with the duals or large size singles, the axle load is less than 10 US ton, whereas the grain cart and combine, they exceeded. It's about 30, to 36 ton per axle. Now, the effect of this ton per axle on soil compaction was also similar to the effect of tire inflation pressure. A higher axle load would create a higher compaction, and a higher axle load with a higher tire inflation pressure would create a deeper compaction, which is difficult to manage. So in either case, the simulation exercise is load is applied with a certain assumption on a footprint of what that load would create, and that load is converted to stress depending on the soil properties. When the soil is wet, the compaction would go deeper. When you have a high tire inflation pressure, your contact area would be smaller, so it would create a high peak load, which translates to a high pressure at the ground, and it goes propagated to the soil. So heavy axle load from grain cart on single axle combined with full tank created 2 to 3 times induced soil compaction as measured through the vertical strain compared to the stress predicted under dual tractor tire centers. Both grain cart and combine front axle created deeper compaction, which is about 12% higher than the compaction at the shallow, which is 6-inch steps. What this modeling and simulation exercise allows either growers or researchers comparing different scenarios on the induced soil compaction. The accuracy of this prediction, either in the soil stress, which is how much stress is propagated to the soil, or how much is created in soil strain, needs further research, including the accurate measurement of footprint, which there is no standard, but we're trying to standardize that at Iowa State, and then creating a soil model properties for a typical cases of corner condition soils that are highly compactable, very sensitive to soil wetness for a compaction. So it gives the opportunity on creating a decision support with some research supporting it would give a higher prediction accuracy. When it comes to the effect of soil compaction or tire inflation pressure management on crop yield, we did a field study on 3 years corn on corn, measuring soil crop yield and soil physical properties as a way to translate the knowledge of machine systems, modern machine systems, under practical planting operation conditions. I'll skip this, but the main takeaway from this is newer tire technologies are emerging. There's a lot of precision agriculture technologies for tires. It's really precise management of tire inflation pressure for a given tire, for a given load, for a given speed. And there's a limited studies on how to evaluate this newer tire technologies that allows a higher deflection, relatively a higher contact area, more contact area than the standard radial tires with proper tire inflation pressure management on crop yield, vehicle productivity, performance. There's always a question on, from literature or from this study that I will share, what's the effect of soil compaction on crop yield? It varies. It varies on the soil condition. It varies on the size of the machines. It varies on how the load is transferred at the ground, how much of it is applied, expressed in stress, and the climatic variability and the crop varieties. But overall, from so many studies, it shows that the compaction induced yield loss could vary 4 to 20%. There were studies done in Canada and Purdue that had shown about 50% yield loss, compared to traffic versus control. But really, the type of traffic that were applied in those studies are not like a typical farming traffic. The traffic was done to create excessive compaction on 100% traffic side by side, which is not always the case. But it was a good study that would show that, there could be a yield loss up to 50% compared to control. The estimated cost of soil compaction, roughly we're looking at about $40 an acre if it's not properly managed. There are studies that show there could be about $1 billion loss in soil compaction. So the cost estimation does not necessarily be only the crop yield decline. It may also account for, if you have a compacted field, you would need to till it. So the cost of tillage would also be considered to get an accurate estimate of the cost of soil compaction on cost. If compaction is buried deep below a tillage, even there's freezing and thawing on a lot of these temperate soils, the compaction could remain even 5 to 10 years or even more unless there are conditions, so microbial activities or soil structure remediation that would try to remedy the excessive deep compaction. Any kind of compaction applied in the field will create a higher tillage energy, time needed to decompact it, and the cost that's associated with it. But our study focused on central commodity field seed hoppers with planting operation at 3 tire inflation pressure treatments, and the study was done on soil compaction measured by compactometer and crop yield. Specifically, what I'm presenting here is 3 tire inflation pressure, which is that row crop tractor equipped with IF tires both on the front and dual, and a planter equipped with VF or very high flaxion tires on crop yield and soil compaction measured by soil cone penetrometer or reported as soil cone index and soil bulk density. Study was done at Iowa State on a 4 hectare. Now the tire inflation pressure treatments, which we did in 3 replicates, is shown here. One of them is standard, that has a high tire inflation pressure, IF on the tractor tires, VF on the planter, and CTIS being the low. First machine where weighed was the planter folded, and that represents a high tire inflation pressure setting for road speed, and that is classified as a standard treatment or high tire inflation pressure. So on the front duals, we're looking at 15 psi. On the rear duals of that tractor, 34 psi. On the planter tire center, 70 psi. On the planter, which is 24-row planter frame, there are also wing tires, and they were set for 50 psi. So for road, really the 50 psi would be when it is unfolded. If we look at the IF and VF, what that is, so if you have IF or VF, new tire technologies that have a different table of tire inflation pressures for the road condition, you would have 11 psi on the front, 22 psi on the rear. On planters with a VF tire on them, 42 psi. The CTIS, which is a low setting, what that is the load and the speed was calculated based on that 24-row planter is unfolded in a field condition, trying to do planting operation with the row unit downforce set to like 200 pounds to create the right seed to soil contact and the depth control. So 24-row planter is unfolded. The weight distribution is used on the front and rear axle of that tractor for a planting operation of 5 miles per hour. So if you have a central tire inflation pressure system that you could regulate or control the tire inflation pressure for field condition, field load, field speed, you would have 11 psi as compared to 15 psi on the front of the tractor rules, or 14 psi on the rear was the central tire inflation pressure, 34 psi on the rear of that tractor for high, which is road condition and road speed. So that's how we created the three cases of tire inflation pressure settings: high, mid, and low. For treatment naming system, we call them standard, IFVF, and CTIS. Okay, the field for this central field planter soil compaction study. During the planting operation, the tractor and the planter system were moving at 5 miles per hour. The seed tank of this 24-row planter was full, and row units were down at 200 pounds downforce. Planting was done perpendicular to tillage. For tillage management, there was a fall tillage and also spring tillage before planting. The yield data that I will present here is for the planter center zones. The 6 of the 24 rows will be row 10, 11, 12, 13, 14, 15 that had seen the different tire inflation pressure treatment of the study. The result that we found, the standard tire inflation pressure setting, which is a high setting, again, that refers to road load condition and road speed. With that tractor pulling that planter from road condition, had the lowest yield, and the IFVF and CTIS had about 4.34% higher yield, with IF and VF 4.51% higher compared to the standard crop yield, the standard tire inflation pressure treatment crop yield. Result is in bushels per acre, and we're looking at 9.2 and 9.6 bushels per acre higher if we manage the tire inflation pressure and use the newer tire technologies. So the letter shows that this is statistically significant at 5% error, or the confidence is 95%. Now we look at the tire inflation pressure effect on crop yield. That gave about close to 4% higher compared to the standard tire inflation pressure. What I will present is the effect of this tire inflation pressure treatment on soil compaction measured by soil con index and soil bulk density. The result here shows the soil bulk density effect. So the tire center, which is trafficked, that had about 1.53 megagram per cubic meter from the high tire inflation pressure, had statistically higher bulk density than the same standard tire inflation pressure at the untrafficked, which is a tractor center line, or a pinch row that's between the duals. We also saw similar statistically significant higher bulk density from the trafficked for the IF, VF, and CTIS compared to the untrafficked or tractor center line. But when we look at the soil bulk density at 6 inches or 15 centimeter soil depths, we classified that as shallow. There were no statistically significant differences among the three tire inflation pressure settings of standard, IF, and CTIS. When we look at the soil cone index, which is reported in kilopascal, again, the trafficked, which is the tire center line, had statistically higher soil cone index compared to the untrafficked or the pinch row from the standard radial tire. So trafficking created a higher soil cone index on the top 0 to 15 centimeter or 0 to 6 inches. Similarly, we saw a higher, statistically higher soil cone index, the top 0 to 6 inches from IF compared to the same IF but in the untrafficked lane. There were no significant differences between the untrafficked and the pinch row for the IF. But when we look at the standard tire inflation pressure in soil cone index, the pinch row had a higher soil cone index statistically than the untrafficked. So the pinch row that had 715 kilopascal is significantly higher than 540. When we look at the CTIS, similar to the standard and IF, on the top 6 inches, the cone index from the traffic had statistically higher soil cone index compared to the untrafficked and pinch row. The pinch row was also statistically higher than the untrafficked. In summary, with modern tractor for central field commodity planter study, the effect of tire inflation pressure that has 3 settings: standard radial tire pressure treatment, where the tire inflation pressure is set for road speed, road load with a folded planter, 24 row, 30-inch row spacing planter, had statistically lower yield compared to the CTIS system and the IF radial by 4.5% and 4.3% respectively. When we look at soil compaction, trafficked for all tire inflation pressure treatments created a higher soil cone index on the top 6 inches compared to the untrafficked. Even though there were no significant differences in the traffic by tire inflation pressure treatments, the magnitude of soil cone index were higher from the standard compared to the IF and VF settings and CTIS. The lowest was measured from the tire inflation pressure of CTIS system. Again, that CTIS system we simulated where you would change the tire inflation pressure if you know the field load for a field speed for planting operation, where the 24-row planter was unfolded. With this, I think the overall conveying message here is field study on crop yield need to be done to quantify the effect of soil compaction for machinery operation for modern settings. You would need to do it at least on a 3-year study to see the effect properly, and the benefit of tire inflation pressure management on crop yield showed about 4% a higher yield compared to a high tire inflation pressure settings with mimicking the standard radial tire. I want to thank overall the collaborators and sponsors on the study that we are doing on soil compaction, modeling approach, or indoor laboratory testing of compaction, and field study of soil compaction from machinery, from cultural practices under a climatic condition at central Iowa, I want to give thanks to all the sponsors of this kind of research that we're doing at Iowa State. And I thank you.